Lord is risen. Hallelujah, hallelujah. Truly he is risen. Hallelujah, hallelujah. Okay, good. So let me sort of check here. Okay, some people are late here to the party. Okay, so what did you have to do here? Page 275, number 347. Okay, so explain why it is relatively easy to remove baked potatoes from a hot barbecue without a hot pad if they are wrapped in aluminum foil. So, why is that, guys? Anyone? Yeah, Max.
Is it because aluminum is a good insulator?
No, it's not an insulator.
Wait, really?
It's not. Aluminum is metal, right?
But I searched it up and it said it was an insulator.
No, it's not aluminum. It's because they wanted to say probably that it keeps the heat in. That's probably what they're looking at. But no, it's not. It's certainly not an insulator. Definitely not an insulator. Okay. That's good try though. Okay, anyone else? Oh, no, let's say Patrick here. Patrick, come in. All right, Patrick. So number 3, why? Patrick. Yeah. So number 3, why is it easy to remove baked potatoes if they're wrapped in aluminum foil?
I didn't do the homework this weekend.
No, that's really bad. Sean. So why number 3? Sean Yu. I'm gonna ask Sean Yu. Yeah, Sean. Yeah, I'll come back to you, Timothy and Leo. Sean. All right. So can you hear me? No, I cannot hear you. Okay, here. No, I cannot hear. Well, Ernest. Not Ernest. I'm asking Sean. Okay, Sean. Okay, so I'll just type the answer. Yeah, you have to make sure that your mic are working, guys, because I think this is so bad. Okay, Timothy.
Is it because aluminum has a high specific heat capacity, so it doesn't?
No, it's a very low. It's a very low specific heat capacity. Leo.
It's a thermal conductor, so it can.
Okay, good. It's a good thermal conductor. Next, what's the other reason? Yeah, Leo.
It allows the heat to transfer easily to the potato.
Okay, and also, Madav.
The heat is reflected away.
No, yes, there's this, but there's one more. There's one more, Aditya.
It also like cools faster than the potato.
Yeah, why? Exactly, why?
Because like it's really like thin.
Well, okay, yeah, there's this, but why is it? I'm looking for one, Ernest. 1 or 2, 3 words.
Low specific heat.
Yeah, it has a low specific heat capacity. It doesn't take a lot of thermal energy to raise its temperature, or vice versa. It doesn't take a lot of. You don't need to remove a lot of thermal energy for its temperature to go down very quickly, right? So there's 2 reasons: because it has a very low specific capacity, and it's a good conductor also of heat. So very good. Okay, so 4, 2 equal mass. Benjamin, you're next for this one. You can mute yourself, Sean. Okay, Benjamin, 2 equal mass samples of copper and iron heated with the same amount of heat energy, should have said like thermal energy, will achieve different temperature. Which sample will reach the higher temperature and why?
Oh, sorry, just got in. I'm not so sure where we're at.
I cannot hear. What did you say?
I just got in the call. I'm not so sure where we're at right now.
Okay, homework, page 275. Number 4. I'll be back to you. So you have number 4. Okay, 7. I'll be back to you as I said. So 7. Why is copper used to cover the bottom of many commercial pots and pans? The stove top. Yeah, Max.
Is it because copper has a low specific heat capacity value.
Well, it's not so much this. It's a little bit of this, but it's another
and also
property.
because it's a good conductor.
Yeah, because it's an excellent conductor of thermal energy. So that's the reason why. It's one of the best. Usually, not always. Usually, those that conduct electricity well, usually they're very good at conducting heat. But it's not always true, but very often. Okay, Benjamin, number 4.
Yeah.
Yep.
Iron, because it has a higher specific heat capacity.
Okay, what specific heat capacity again, Benjamin? Do you know? What does it measure?
It measures. I'm sorry, I'm trying to find the definition in my notes right now.
What did you do over the weekend? You played Animal Crossing? What did you do?
No.
No. Okay, David, I'll be back to you. Yeah, David. Yep. 1 kilogram. That's correct. Okay, so yeah, sure. Yeah. Very good. Yes, excellent. Right, it's going to be copper. Right, for the same mass, same amount of thermal energy. It's just like the equation. So if I go back here, I'm going to share a screen like very quick here. Okay, so let's share the screen. I could have used a whiteboard, but there we go. Scrap. There you go. So this is your equation here. Remember? Whoops. Q is equal to mc delta T. So in both cases here, like this term is the same amount, same mass. So what will determine, of course, like the raise or in temperature will be C or delta T. And you can see here that they are inversely proportional to each other. If I put like the delta, all of this on the other side, I'm going to have delta T. So Q over M over C, right? Whoops. So you can see here that delta T is inversely proportional to specific capacity. So since copper has a lower heat capacity, then the change in temperature will be greater. Okay, good. Now I don't want to see myself here, so let me put this here. Okay, what's the other one here? For 8. Okay, so you're spending Labor Day weekend at the beach and turns out to be clear, hot day. Use the concept of heat capacity to describe which warms up faster, the water or the sand. Which of the two will cool down faster at night? Okay, David again. There you go. Mm-hmm. Yeah. Good. Very good. Excellent. So in the morning, yeah, hold on a second, Max. So let's say here, like the sun is out, it's a super hot day, and by the time you go to the beach at 1 o'clock in the afternoon, both the water and the sand has received the same amount of thermal energy. But of course, since sand has a lower specific capacity, so it takes less thermal energy to raise its temperature, right? So the sand will be like super hot. Whereas the water will still like be a little cool, and then at night it's the other way around. It takes very little thermal energy for the sand for the sand temperatures to go down, right? So at night the water now is kind of cool. It's kind of warm, but the sand will be cool. What is that? There's also another reason, of course, like there's more mass of water than there is of sand. That's another reason. But if you had the same mass of sand, the same mass of water, this is exactly what will happen, right? So during the day, the water will be cooler and the sand will be hotter, and the night will be the other way around. Yes, Max.
Oh no, I was just gonna ask if I could if like for my answer, because I said the water is big and this compared to the sand,
Yeah,
like the
yeah.
ocean.
They're looking more for the specific capacity, so that's not bad. Nadav.
When we have multiple factors at play, is giving any of them correct,
Yeah.
or
You have to sort of look at what they're looking for. I guess in this case, it's probably more the specific capacity than the mass of anything. Okay, so I know it's since it's a yeah. Okay, what's the other one here? So so 24 to 29. So any questions? Any question? You got them all? Very good. I am waiting. No? Yeah? Okay. All right. Okay, so let's start here. So let me go back to my board here. Stop sharing. I don't know why I cannot see it. Okay, let me sort of share this again. All right. All right. Okay, let's go back to this here. All right, so don't write this down here. I'm just gonna ask some questions here. Okay, so just listen. So once again, don't write it down. It's not important here. Okay, so let's suppose here that we have a plane. We have a box right here at the bottom. And let's say here, like, this is like 60 degrees Celsius. And the plane is 20 degrees Celsius. All right. Now, let's pretend here, all of a sudden, right? All of a sudden, what you see is you see the box going up. And as it goes up, the temperature goes down. Okay. And this one, it could sort of go down also a little bit. Okay. All right. So all of a sudden here, once again, all of a sudden, you see the box starting to go up. And then as it goes up, it loses like thermal energy here. Now I'm going to ask you questions here. Does this situation here, does it violate, it means like, does it break down conservation of energy? Does this situation here breaks down conservation of energy? Okay, some other people here, I'm just waiting, some other people, it's always the same people. Max, no, Max again. Okay, Max, there we go.
Oh, okay. Is it no because there's also like other forms of energy at play?
Okay.
Like for example, like there's also like as it goes up, it builds up gravitational potential energy.
Okay, good. All right, so that's the key point here. So this situation here, situation right here, very good. As it goes up here, it gains gravitational potential energy. It gains also a bit of kinetic energy, but it's mostly like gravitational potential energy. And what happens here, it comes at the expense of thermal energy. So energy is conserved here. There's no problem. Energy is conserved. Now, my next question is, why are you not going to see this happening? Why are you not going to see all of a sudden like a hot block going up in a plane? Why is it that you're not going to see this happening? Does anyone have any idea? Because from the point of view of energy, this is quite valid. Yes, Madav.
is it because there aren't any external forces?
No, they are. Okay, so it's good. This is a good point. All right, if the box needs to go up, it has to come as a result of an external force. Where is this external force going to come from? Where's this external force going to come from? Come on, some other people here. Not always the same. Stephen. It's always the same though.
Wait, is it so? It has to be a force like
pushing it up, right?
No. Oh, yeah. Okay.
No.
So where is it gonna come from?
Like, isn't it just like an applied force?
No, there's no applied force. I'm saying there's this.
So it's just going
okay?
up by itself?
Yes, yes. And I asked, like, is it possible from point of view of conservation of energy? And you answer, well, Max answer, yes, it is possible. There's conversion of thermal energy into gravitational potential energy.
Okay, I have no clue.
You have no clue. All right. Anyone else? Just try it. David? No. Okay. All right. Okay. Hold on a second here. Okay. This block here is in contact only with the plane. All right. So where's the force going to come from, guys? On the block. Yeah, Madav.
The plane.
Very good. It has to come from the plane. In order for this block to go up, so now we're going to do here, we're going to look at a little blown up of this. Okay, so let's see here, this little region here. All right, and then, so this is the, this is the block here, right? This is very, very big. This is the plane. Whoops, this is the plane here. So at the microscopic level, it's not exactly smooth, right? It's a lot of valleys and peaks, and that's where friction comes from, actually. All right, now, if this block is to go up, it has to come from the plane. It's the molecule of the plane that will sort of push on, collide with the molecule of the block, right? Now, why is it here, once again, that you're not going to see this happening anytime soon, even if you were to wait until for 10 billion years? Yes, Madav?
Is it because the molecules are interacting in random directions instead of going up?
Very good. Excellent. I don't know if they had the same idea, Day?
I did not know.
No. Okay. So this is very important here. The kinetic theory of matter tells you the following. It tells you that matter is made up of tiny particles, either molecules or atoms, that are constantly in motion, but this motion is random. That's very important. It is random. All right. In order for this block to go up here, in order for this block to go up, you would need all the molecules here, right, in the plane, and perhaps the molecule in the block to be going all in the same direction, right? So to give a net kick up, right? So you will need, like, let's say, go in the plane here, right? So you would need like all the molecule in the plane to go in the same direction and to collide with the molecule in the block. All right. Is it possible? Yes. Is it likely to occur? That's the key point here. So from the point of view of energy, this can happen, right? You can have like all of a sudden a hot object. Let's say here I have, all right, so I have, let me see here. There we go. So this is hot. I put it here and all of a sudden, whoops, it goes up by itself and lose temperature, right? Lose thermal energy. It's possible. It's possible. From a point of view of energy, this is possible. Is it going to happen? No, because for this to happen, you would need like all the tiny molecules of this pad here to be going all in the same direction. And the likelihood of this happening is infinitely small. All right? Infinitely small. Just to give you an idea of how infinitely small it is, let's say here, like the plane here has two motion, either this way or that way, up the plane, down the plane. So let's say here you have 50% chance it goes this way, 50% chance it goes that way. All right. Now, if I'm asking you, what are the odds that two such molecules are going in the same direction? Not always, Max. Day.
A quarter.
A quarter. All right. How about like 3? What are the chances that all 3 will go in the same direction? Day.
An 8.
What? How much?
1/8.
1/8. Okay. So what do you do here in order to get this?
I just do 1/2 to the exponent of however many particles.
Very good. Excellent. Now, let's pretend here there's only, let's pretend there's 100. Let's pretend there's 100. Now, I want someone to put this in their calculator and gives me the odds of, and there's way more than 100 molecules, right? Way, way more. But tell me, like, put this in your calculator and tell me what are the odds of 100 such molecule going in the same direction. Tell me what it will give you. Your calculator. Okay, some other people. Leo.
7.8, 8 times 10 to the negative 31.
Ah, very good. Even if you were, you know, if you toss a coin, right? Let's say every second. Okay, after a long time, you have 50% of chance it falls on tail, 50% of chance it falls on the other side here, right? Now, if you had this situation here, you have 100 molecules here. And let's say there's a trial like every second, all right? So 1 second, whoops, one goes this way, one goes that way, one goes this way. Whoop, other second goes this way, and then there's another configuration. Since the Big Bang, there's been less than, I think, like 10 to the 28 seconds has elapsed since the Big Bang. So even since the Big Bang here, the chances of having like 100 molecule going in the same direction is still like super low. All right, it's super low. So that brings us to the idea of thermal energy that's different from the other energies here. Does anyone had like questions here? Some people had some questions. No. Okay. So heat, you remember here? You remember I told you like so go back to your notes here. I told you to leave this by itself. Heat is nothing else but work done at the microscopic level. However, this work can never be 100% efficient. All right. So let's see. So, however, this work can never be 100% efficient, owing to, whoops, that doesn't look like a owing here. Yes, Manav.
What does it mean by efficient?
What's that?
What does efficient mean in this context?
Well, it means like you don't get like the full output, all right, of work. This work can never be 100% efficient, owing, whoops. I'll give you a second. I'll give you owing to the random motion. Of a tiny particle. All right. All right, so you don't have to, I'll come back if, you know, right? What's that? Okay, let's see, you don't write this down here. All right, like, let's say here, a steam engine here, all right, like Titanic. They want to sort of move the propeller, the big propeller. When they do this, they have a piston, little piston right here. Don't write this down here, this is your piston here. All right. Now, if I want to do work on the piston, I can push on it. And when I push on it, I make sure that all the molecule in my hand here, all the molecule in my hand, my fingers, they're all going, I know there's a random motion. But there's also superimposed on this, there's also a net translation in this direction, all right? So this is like 100% efficient here. All the molecules here are going in the same direction with my hand. Now, what do they do with steam engine? What they do with steam engine is that they warm up water and they turn into steam, which is nothing else but air molecules, right? In the gas form. And what they do here, those air molecules here, they will collide with the pipes. Some of it will collide, right? But they will not collide all in the same direction, right? So collide like this, some will go there, some will go there, right? And this is the key point here. The work done by the steam cannot be 100% efficient. You would want all those water molecules here to be going all in the same direction. That's not going to happen. You can't do this, all right? From the point of view of probability, you just can't do it. So although you would love all those molecules to go this way, unfortunately, some of this work will be used to raise the temperature of the pipe, which you don't want. You don't want to raise the temperature of the pipe. You want to move this darn piston, right? But that's not going to happen here, right? So some of it will go into raising the temperature of the pipes, raising also the temperature of the piston, which you don't want, right? So this is the key point here. This is what I mean, Madav, by not 100% efficient, okay? So we're going to learn this about next year. We're going to go back to this when we're going to do thermodynamics and look at steam engine. And perhaps you may have heard the term like second law of thermodynamics. Well, this is where it comes from. Max.
Sorry, so at the microscopic level, so the particles, due to their always random direction of motion, so the work that's being performed can at the microscopic level can never be.
Yeah, it cannot so what happens here is that when I'm going to show you in a second here, when you put a cold and a hot body together, right? The only thing that can happen here is transfer of kinetic energy from the hot body to the cold body. The only thing it can do is raise the temperature, right? Raise the temperature of a colder body. It's not going to make the colder body go like crazy, right? Like it's not going to change the mechanical energy of the whole body as a whole. It's going to change the thermal energy, microscopic mechanical energy of the object. Yes, David. For what? For example, what? Yeah. Yeah, like it is. Like, so what happens here is that, so what happens here, the air molecule will collide with the molecule of the pipe and will sort of cause them like to shake a little bit more. So it's going to raise the temperature of the pipes, right? Of course, the air molecule, the water molecule are not going to go all the way up, right? They're not going to push the darn piston pipes up, right? So the only thing they can do is change the kinetic energy of the molecule, kinetic energy of the molecules of the pipe, and it's still random. So only the thermal energy, only the temperature will change, right? Temperature of the piston will also go up, but you would love to have all those molecules here going in the same direction, but it's not going to happen, right? If they were able to go all in the same direction, then like the thermal energy of this piston will stay the same. It's just like the whole mechanical energy of the piston that will sort of increase, right? The kinetic energy of the whole body, the whole piston will increase. Right? At the microscopic level, perhaps, but once again, it's probably very inconsequential and still very improbable as well. Okay, probability, we look at only two motion here, only one and back up the plane, down the plane, and we saw like how unlikely it is for those molecules to go in one direction, all in the same direction. So imagine when the molecules are able to go in also all possible directions. So it's virtually like impossible. Yeah, Max, we're gonna have to move though. Yes.
Okay. So so obviously like it comes down to probability, but also like
Yeah, that's correct. That's come down to probability. Yes.
Since particles are in random motion, like in theory, if I have like a bottle here, and like the 0.0000 like a million zeros, the chance that all of them align, the bottle can just start moving on its own, right?
Yeah. It's not gonna happen. Even if you let it sit since the Big Bang, it's not gonna happen, right? The chances, it's unlikely, super unlikely to happen, so much so that it's virtually impossible. All right. Okay, good. So let's go back to this here. So, okay. So, so thermal energy is transferred between a cold and hot body. Oh, I don't know. I don't like my English here, but anyway. Suddenly it's transferred between a cold. Nah, erase everything. Sorry. I know it's easy. Yeah. Okay. So when putting in contact a cold body, and put in contact a cold body with a hot body. Okay, only thermal energy can be exchanged. All right. So if you have here, you have 20 degrees Celsius and 40 degrees Celsius. Okay. So what will happen here, you'll have transfer of thermal energy from the hot to the cold body, raising the thermal energy of the colder one and decreasing the thermal energy of the hotter one. So increasing the temperature of the colder one, decreasing the temperature of the hotter one until they reach a thermal equilibrium, and they reach a common temperature called equilibrium temperature. All right. So due random nature, molecular motion, right? You will not see the following happening. Happening. Is there 2N happening? Again, happening. I don't know. Anyway, so you will not see this. You will not see should be the same dimension here. Okay, so you will not see this block here going this way and this block here going that way. Okay, and in so doing here, they pick up kinetic energy as a whole, and then and then thermal energy went down, right? Like let's see here, like this one like goes to 30 degrees Celsius, right? And this one goes to, I don't know, like 18 degrees Celsius. So you will not see this happening, okay? Okay. Although from a point of view of conservation of energy, this is possible. It's truly possible. Okay, but it's unlikely. Okay, so you cannot have Q converted into pure work. Okay, cannot have this pure microscopic work. Microscopic. And this is called like the second law of thermodynamics. So we're going to learn this next year. Dynamics. All right, you good? Okay, so by the way here, like there are 3 ways that thermal energy can be exchanged. You should have taken notes about this. So what are the 3 ways that thermal energy can be exchanged? Yeah, Nadav? Always the same.
Convection, and radiation.
Yeah, very good. All right. So 3 ways that thermal energy can be exchanged. All right. So conduction, convection, and radiation. All right. Now, what's so special about radiation is that radiation does not require anyone. Radiation does not require what? Anyone? Okay, some other people. Jeffrey, there we go.
A medium.
Yeah, a medium, or does not require a contact. That's correct. All right, does not require contact. Okay, the Earth is being warmed by the sun, and yet the sun is not in contact with the Earth. All right, require contact. Okay. Now they're yelling at my dog. Yes, well, it's not my dog. My daughter's dog. Okay, and conduction. So what's the difference between conduction and convection, guys? What's the difference between conduction and convection? Conduction and convection, or what's the same too?
Is it that conduction requires direct contact and convection is through?
No, both of them require contact. So both of them require contact. Okay, someone else. Come on, it's always same people. Eric, there we go. Eric G. All right. So what's the difference between conduction and convection?
Can you hear me?
Yeah, I can hear you.
conduction is like transferring by like particle collision.
So does convection.
Oh.
Okay, all right. So both of them require contact here. So both of them here require contact. Convection here occur when this is like conduction. It's conduction. But one substance is a what? Is a Marav?
Fluid.
A fluid. Very good. Okay, so fluid is gas or liquid. All right. Whoops. So yeah, Max.
So if I dip my hand in piping hot water, then it's convection.
Okay, so here's the thing here. Like there's a solid here. So let's put the two solids here. Don't forget in solids, the atoms cannot move. They just vibrate. All right. So if I put two solids here, one is hot, one is cold. So the hot one moving faster, they're going to collide with the slow moving molecule of the colder body, transferring the kinetic energy, and then it's going to vibrate more. The temperature of the cold will go up, temperature of the hot one will go down, right? Okay, convection, at the moment, well, I don't have it, but I have a heater. I didn't turn it on, but I have a heater under me. When I turn this on, I do not put my feet in direct contact with the heater, but I will still feel thermal energy to my body here. How does it work? Because what happens here is that there's a heater here, the metal heater, there's the water, air molecule. So air molecule will come in contact with the hot plate of the heater. The molecule of the hot plate will transfer some of its kinetic energy to air molecules. And now the molecule will pick up kinetic energy, but it's air. It can not only vibrate, it can move over long distances. So here, so you got your air molecule here that is moving like faster. It can travel long distances and collide with another air molecules, transferring some of the kinetic energy and so on and so on. So this is what convection is. It's nothing else but contact, but one of the object is a fluid. So the additional kinetic energy picked up by the molecules by the tiny particle can be carried over long distances, right? So this is why, like when the air molecules are hot on the bottom, eventually it will transfer this extra kinetic energy to the other air molecule throughout the whole room. And then we say that the room is being heated by convection, all right? So that's the way it is. So you knew that, right? Okay. So once again here, so these require contact, right? Well, so we'll put this here. Both conduction and convection require contact. Contact. Now that's kind of interesting here because let's say you're in space. You have a block, a hot block. You let it float in space. It's not going to be able to make contact with anything. There's nothing in space. So what will happen to the block? Will the temperature of the block stay the same, or will it cool? Now you might think, well, it should cool, right? Well, how is it going to cool? Anyway, I'll let you think about this. Perhaps you can give me the answer next time. Okay, so let's go to the big crux of today's lecture here. I know Catherine wants to go and eat, so let's do this like quick here. So heat exchange. Heat exchange. So if you have a harder body here, and in contact with a colder body. Thermal energy will occur and it will go from the hot to the cold. That's probability 2. Okay. Now, if the system is thermally isolated, then the the thermal energy gained by the colder body will be equal to the thermal energy of lost by the hotter body. So then thermal energy lost by hotter body will be equal to the thermokinetic energy gained by colder body. All right. And this situation will last until they both reach the same temperature, same final temperature, called the equilibrium temperature. Right, that's by conservation of energy here, right? So by conservation of energy. Now, something I forgot to mention here is this. A couple of things I'm like. So when Q is greater than 0, the body absorbs thermal energy. When Q is smaller than 0, the body loses thermal energy. All right. So since the hotter body is losing thermal energy, its Q will be negative. And this one here, since it gains, the colder body gains thermal energy, Q will be positive. So if I use the sign, what I get here is this. The heat lost by the hotter body will be equal to the thermal energy gained by the colder body. And I'm going to call this like H and C. And this is called the heat exchange formula. All right, it's very simple. Come on, we used to teach this to a long time ago. We used to teach this in grade 10 science. Now you're learning optics, which is not bad, although it's not going to be useful much. This would have been like a lot better. Anyway. So that's the heat exchange formula. Okay. So let's do an example. So example. We're going to have a container here. All right, so it's a container made of iron. All right. And then I'm going to use orange because if I use yellow, you're not going to see anything. And then we're going to have a piece of gold. Piece of gold. Let's see, this piece of gold is at, so gold. And let's see here, the piece, let's see, it's a temperature of 200 degrees Celsius. All right. Oh boy, computer is starting to, and this is water. Okay. There you go. And what we do is we put the gold into this container with water, we close the lid, and the question is, what's the final temperature? What's the equilibrium temperature of all this? Okay, so the question is here. Let's say a 20 gram gold coin at temperature of 200 degrees Celsius is placed into, let's say only 100 gram of water at room temperature. 20 degrees Celsius. The water is in a, let's say, 3 kilogram iron container. Find the equilibrium final temperature of the whole system. After some time after you close the lid. It's a long lesson today. All right, so you have the piece of gold here, gold coin. Put this in, oh, I didn't say, like, yeah, 100 gram of water, 100 ml. It's roughly like density is roughly 1 gram per milliliter, roughly. Okay, the first thing you have to identify here is what is the hotter body and which one is the colder body. So let's look at the hotter body here. So which one is a hotter body here? Come on, quick, Stephen.
Gold.
Gold, very good. Right. and it's AU, right? That's a sample here. What is the colder body? David? Yeah, but it's not only the water. That's correct. So the colder body is here. It's both, right? We pretend here like water has been sitting in this iron container for a long time. It has reached thermal equilibrium, right? It's water, right, plus iron container. And iron container is Fe, right? All right, so the rest, it's not really difficult. This it's just like it's a little long, but it's not really difficult. Okay, so what we use here, we're going to use the heat exchange formula, right? So this formula right here, we're going to use the heat exchange formula. So let's put this here. So, whoops. So minus QH is equal to Q colder body. Now, what's the hot body? The hot body is the gold. I'm using your U. The colder body, it's the water plus the iron container, right? Now we're going to use our formula. So this is going to be equal to the mass of the iron times the heat capacity, specific heat capacity of the iron, times the temperature, the change in temperature of the iron, is equal to the mass of the water times the specific capacity of the water times the change in temperature of the water plus the mass of the iron plus the specific capacity of the iron times the change in temperature of the iron, right? So what do we know? Well, let me sort of put this, let me make it like a little bit more here. So here it's going to be minus the mass of the iron times the specific capacity of the iron times the final temperature, which is the same for everyone, times the initial temperature of the iron, gold, is equal to the mass of the water times the specific capacity of the water times the final temperature minus the initial temperature of the water plus the mass of the iron times the specific capacity of the iron times the final temperature minus the initial temperature of the iron, right? So where the initial temperature of the water is the same as the initial temperature of the iron, which is, of course, 20 degrees Celsius. What else do we know? Well, we know the initial temperature of the gold. Initial temperature of the gold is 200 Celsius. We know the mass of the gold, which is 20 grams. So we'll put it in kilogram. The mass of the water is 100 grams. So we'll put it in kilogram here. And the mass of the iron is 3 kilograms. Now you would be given like the specific heat. Now if I go according to this table here, so let me see here. Gold is 130 joule per kilogram per Celsius. Iron is 460. And then the water is 41.8. Okay. Now, my dear friend, it's just math. You just put everything in, just math. There are ways of doing this like a little faster. There are ways of doing this like a little slower. So what I'm going to do here is I know that these two terms here are exactly the same. So I'm going to sort of factor them out. All right. So here, this is Ti here. So if I factor them out, what I get is I get this. Times, because I don't have space here, TF minus TI. All right, I just factor this. By the way, this thing here, I'll talk to you tomorrow. This thing here is called the heat capacity, not specific heat capacity, the heat capacity. Okay, and then you put everything in. So let's do this happily. 0.02 kilogram times, let's see, 130 joule per kilogram per Celsius times TF minus 200 degrees Celsius. All right, that's the first one. So I'm going to continue here because I don't have space. This is equal to 0.1 kilogram times 4180 joule per kilogram per Celsius plus 3 kilogram times 460 joule per kilogram per Celsius times TF minus 20 degrees Celsius. All right, so let me do this in my head here. So 2 times it will be 260, so it will be like 2.6. If I do something wrong, let me know, okay? So here, kilogram cancels, and you're left with 2 joule per Celsius. Okay, if I do this like very quick here, so it's 480. This one is a little bit too much, so I have to do this in my head here. So 3 times 460 plus 41. There you go. So this one here gives, whoops, this gives me 117.98 joule per Celsius. Then my friends, you can do whatever you want here. You can divide, you can bring this here, and then isolate for TF. It's a little bit long here, but that's what I said. If you want to distribute, you can distribute. So let's do this here, 2 Celsius here. I'm going to do this like very quick here. Minus an enemy of enemy is a friend. So times 2 will give me 4.2. So I think that gives me this, if I'm not mistaken.
It's 52, right? It's 52, right? It's 5.2.
20, was that?
It's 520, right?
2.6 times 200? Oh, okay. Sorry, yes. 520, right? Okay, so 520. Okay, so this one will be like this. Minus, so it's going to be twice. Oh, I'll use my calculator here. So 1798 times 20. So, oh boy. Joule. And now we're going to collect the TF and the C. So I'm going to bring this on the side. I'm going like very quick here. I'm going to bring this this one here on that side, change the sign. Now this one here will give me plus 520. So that's going to give me like this. This one here will give me 1798 plus 2.6. So it gives this. And then finally, we send this on the other side. Oh, I hope I didn't. I hope I did okay. I put numbers here. I'm not so sure if it's going to be okay. Because I don't want this to be like greater than 100. So this times 36, 480. Yeah, very good. There we go. And voila. So this is the final temperature. It's not very much because of water. Water has enormous amount of very, very high specific capacity. So this is why like most of the thermal energy has gone into the water. So that's why it's not very much more than what it is. Okay, questions? Sorry, Catherine. You might be like already eating. Yes, Madav.
So the water would heat up first and then the iron would heat up. But
No, I don't want you to think about, yes, eventually that's the mechanics of all things here, but like I don't want you to get into like the mechanical, like what's happening, like the timeline here, okay? You just say, okay, this is how much thermal energy I have at the beginning, so this is how much thermal energy I have at the end. How does it distribute this? That's it, okay? Key questions? All right, so I'll see you tomorrow. I'll stay here for 5 minutes if you want to copy a little bit more, and you have like some problems to do, like 4 problems. Oh, by the way, whenever they talk about coffee, maple syrup, anything like this, it's made up mostly of water. So you just use like a specific capacity of water, right? Coffee, it's water. Maple syrup, it's water. Okay. Juice, orange juice, it's water. Okay. So that's what it is. Okay, guys, so sorry for today, and I'll see you tomorrow. Bye.
Bye.
Have a good lunch.
Thank you. Is it Catherine?
Bye, sir.
Thank you, Catherine.